Hello students, this brief tutorial will walk through the 5 most basic reaction types, also highlighting the specific types of composition and decomposition, reminding us of the activity series, just to prepare us for the next video, and that is showing how to create ionic and then net ionic equations. I'd like to talk through the 5 different types and then show us specific examples of the 5 different types. So our 5 types are composition, which is also known as synthesis, decomposition, single replacement, double replacement, and then our 5th type would be combustion reactions. In a composition reaction, 2 or more reactants combine to form one product. So that is what distinguishes a composition from all others. In a decomposition, one reactant is creating 2 or more products. In a single replacement reaction, an element is being added to a compound, and if the element that is trying to replace a similar element, meaning if this element has the potential to become a cation, it will replace the cation in the compound. If it has potential to be an anion, it will replace the anion in the compound. And if it is more reactive and can do the replacing, then we will get an element and a compound back out. For example, if you are adding element A, and element A has the potential to become a cation, for example, a metal, then it will combine with element or compound BX, and if it is more reactive or higher in the activity series, it will replace element B. It will bond with X, and then B will be existing as a solo element. But we can also combine anion and, let's say, compound BY, and if X is more reactive than Y, for example, chlorine more reactive than iodine, then it will take the place of Y. A double replacement reaction is where we add a compound to a compound and 2 things do the replacing. For example, if we have generically AX plus BY, A and B will switch, A going with Y and B going with X. However, this will only happen if one of our driving forces is satisfied. Namely, if we create water, if we create in our products a precipitate or an insoluble compound, if one of our products is a gas, or if one of our products is a molecular compound that will not significantly ionize or dissociate. In combustion, we are reacting a hydrocarbon, for example, methane, for example, let's say ethanol, and that would be C2H5OH, excuse me, with oxygen, so something composed mainly of carbon and hydrogen, which will satisfy the criteria of being flammable, combining with oxygen, and we will create carbon dioxide and water. For combustion, it's just up to us to be able to recognize if it's a hydrocarbon or not. For double replacement, those will work as long as we're satisfying one of the driving forces. Single replacement will work as long as the activity series is being honored. If it is not, for example, if X is not reactive enough to take the place of Y, well then no reaction will happen. However, we need to go through the different types of composition and decomposition. The simplest type of composition begin with adding an element to an element. And you will simply put the cation first and we'll get a compound. So for example, if we heat magnesium in the presence of oxygen, we will create magnesium oxide. +2 -2. If we want to be actually specific and have our phase symbols, any ionic compound will be a solid at room temperature pressure, and to balance the full equation, we would have that. If we would combine sodium in the presence of chlorine, that will form sodium chloride, +1 -1, and we need a 2 and a 2 to balance there also. The next main type is if we react a metal oxide plus water, we create a metal hydroxide. That is also what we recognize as a base. So if we would combine calcium oxide with water, to make it specific, the metal here is calcium. To make it a hydroxide, +2 -1, so we need a 2 to balance. And we would need a 2, and a 2. Oh, that's silly. 1, 1, and 1. 1 calcium, 1 calcium. All 2 oxygen, 2 oxygen, and 2 hydrogen, 2 hydrogen. Didn't even need those coefficients. Let's say we react potassium oxide and water. We're going to form the metal hydroxide, +1 -1, and we would need a 2 there to balance that. Well, what if we react a non-metal oxide with water? Well, in that case, remember, non-metals are opposite of metals, and so what would be opposite of a base but an acid? To be specific, we are going to form an oxyacid. For example, carbon dioxide reacting with water. Remember we saw with Lewis dot structures that we often will lower the formal charge of our nonmetal, the increased amount of oxygen that bonds with it. So if we want to approach these reaction predictions in this way, that carbon, if it can, is going to try to pick up another oxygen. And so if we directly bond the one oxygen from water with CO2 to create CO3, but it's not only going to swap in that oxygen, but also the charge that oxygen has with water. What is remaining but hydrogen? +1, so we'll need a 2 there to balance, and I form carbonic acid as a result. Now, we'll talk about, but something worth mentioning, whenever carbonic acid is formed, it is incredibly unstable. Pretty much immediately decomposes into H2O and CO2. So we actually, as we're making it, it will recreate the reactants pretty quickly. If we would bubble through sulfur trioxide into water, the SO3, sulfur, which we know can exceed the octet, it's going to take on that oxygen, forming SO4, sulfate, hydrogen, +1, H2SO4, and we are balanced as written. What if we react a metal oxide and a non-metal oxide? That is just going to create a salt or an ionic compound. So for example, excuse me, if, let's say, barium oxide reacts with, let's say, SO2, well, non-metal oxide is going to do the same thing it did with water. It's going to pick up an oxygen, forming SO3 in this case, directly picking up that oxygen and also the charge of that oxygen. We then have barium +2, balanced as written. The other, a little bit less common, would be ammonia plus an acid. That creates an ammonium salt, or an ionic compound that begins with ammonium as the cation. For example, NH3 reacting with, let's say, dichromic acid. The ammonia forms ammonium. The ammonia will react away all of the hydrogens from the acid. What we'll have left over is the anion from the acid. Do not concern yourself with the number of hydrogens. That will be worked out through balancing. Dichromate is -2, so we'll need NH4 These charges are now balanced, and we need a 2 there to balance the entire equation. If we would react NH3 with H3PO4, well, that will create ammonium. It's going to react away all the hydrogens. We'll be left with the anion from the acid. Phosphate is -3, so we need NH4,3PO4. And then to balance, we'll end up needing a coefficient of 3. So those are the 5 specific types of composition. Now to the specific types of decomposition. We'll start nice and easy. Decomp of a binary compound. A binary compound will be composed of 2 elements. So, if, for example, we run an electric current through water, we will separate it into its individual elements. When we are writing elements on their own, we always have to check to ask ourselves if they are diatomic. And we know our 7 diatomics, hydrogen being 1, oxygen being 1. So, to balance this, we would need a 2 and a 2. So, a binary compound will decompose possibly into an element plus an element. Well, let's look at the decomp that are opposites of composition. What about a metal hydroxide? Now, not all reactions are opposite of each other. However, in the case of some of our composition and decomp, they are. So, if we decompose a metal hydroxide, we will get out what we use to make a metal hydroxide, a metal oxide and water. So, for example, if we take magnesium hydroxide, we will get out MgO plus H2O. 1 magnesium, 1 magnesium, 2 hydrogen, 2 hydrogen, 2 oxygen, 2 oxygen, balanced as written. If we take lithium hydroxide and react it, we will create lithium oxide and H2O, and we need a 2 there to balance. +1 minus 2, that's our correct formula. If we decompose an oxyacid, we will get out what we use to make it, and that is a nonmetal oxide and water. What I would do with these is to directly take out water. We are going to remove H2O, and whatever we have left over will be the nonmetal oxide. So that is confirming the decomp of this unstable acid. Taking water out, we get CO2. Well, the different unique types of decomp would be metal carbonate. That creates metal oxides plus CO2. For example, calcium carbonate, decomposing that, we would form calcium oxide plus CO2 plus 2 minus 2, and we're balanced as written. If we would decompose, let's say, aluminum carbonate, we will get aluminum oxide and carbon dioxide. plus 3 minus 2, Al2O3, and we would need, let's see, A2, that'll give us 4 aluminum, 6 carbon, so if I put a 6 here, probably going to have to reduce these coefficients, then I would have 9, 18, 6, plus another 12, okay, that would be 18, but I can divide all these out by 2, and so just a 3 is needed before the CO2. If I take a metal chlorate, I will get a metal chloride and oxygen gas. The classic experiment that we did several times in honors chemistry, we decomposed potassium chlorate. We will get potassium chloride and oxygen gas. Plus 1 minus 1, we need a 2, and a 3. If we would decompose, let's say, copper 2 chlorate, we will form copper 2 chloride, so plus 2 minus 1, CuCl2 plus O2, and we will need a 3 there to balance. The other, more rare, just like the ammonia plus the acid is a rare composition, a rare decomp is of a metal nitrate. If a metal nitrate is decomposed, we actually get 3 products. A metal oxide plus NO2 plus O2. For example, MgNO3, 2, we will get MgO plus 2 minus 2 plus NO2 plus O2. 1 magnesium, 2 nitrogen. So if I try a 2 there, 6 oxygen, I have 4, 5, 6, 7. Let's try a 2 there. That will require a 2 there. 4 nitrogens require a 4 here. We will then have 6 oxygen. We have, 12 oxygen. We have 8, 9, 10, 11, 12. I am now going to walk us through a couple composition and decomposition predictions in the next video.